What's up YouTube, it's Jacob from International Precision Engineering, and finally we have the last video of the 4 talking about software correction of machine tools. Again, this video is broken down into 3 parts. We'll talk about doing an error budget, sort of what considerations should you think about when you're sort of planning out this process, what tools are available, which ones should you have, which ones make sense for your application. We'll also talk a little bit about tolerances for sort of applications so you can kind of gauge from that. I'll talk a little bit about how to measure it, and I don't really want to go into too much detail on that because every machine is going to be different, but we'll just really talk about sort of the general theory on that, and then we'll review the software in this specific application. I started with error budget because I think really that's the only difference between somebody who can do this well and somebody who's going to kind of just spin their wheels, is this sort of ability to plan and have the foresight to see ahead and kind of see where they're going ahead of time and then take the path of least resistance, right? And everybody kind of meanders, and that's okay, but I highly encourage this with all things, design, machine building, I mean with software correction, I mean planning, and even project management. Planning is key. If you don't plan, it's not going to go well. So this is sort of the planning process that I use, and it's called an error budget, and it really comes from sort of uncertainties and things, but that's a later video. In short, you're kind of starting from the end goal. It's like, with this machine that you want to software correct, what are you doing with it? So, for example, there's sort of 3 examples here. It's like, oh look, I'm just making pretty pictures, and by the way, like medical MRIs, they only have about 1/2 millimeter tolerance, right? I mean, that's not to say that they can, that all the pictures are distorted and things within that 1/2 millimeter, but from a sort of accuracy standpoint, when they stick this violin in there and at these universities and they think like, oh, we got it, it's like, no, actually you really don't, but you got a good picture of it. You can see what's inside and how they made it and sort of other things, but that's enough. That's enough for a doctor to see like, hey, is your heart there? Is there a tumor on it? And sort of equivocally for 3D printing people, hey, if all you're doing is sort of rapid prototyping things like my face, or like, things that look good, or like coat rack hooks, it's like, that's probably enough for you. So when you talk about interchangeable parts, right, this sort of middle example here, it's like on a 10 millimeter shaft. Okay, so if I was going to make an engine or sort of like a camera part or whatever, right, I have to decide, when I have 2 pieces that fit together, when that shaft goes into the bore or a locating pin or whatever, what type of fit do I want? So this is straight out of the machinery handbook here. Interference fit, right? So on a 10 millimeter shaft, the gap is minus 25 microns, so it's about 1,000th, right? And that means that you're going to make the shaft big and the bore small, so the gap's going to be about 1,000th or 25 micron with a tolerance of 1/2,000 or 12 micrometers, right? So when I make that shaft, I'm shooting for sort of a 1/2,000th over, or 12 or 25 micron over, or whatever. Call it 12 if you want to split the difference. But I also have a tolerance of 12. Okay, so it's about a 1/2,000. This is probably as tight as you want, and think about that. That's a locating fit. That's for like engines and things. It's like how like people at home, they're probably not going to be making anything more precise than this. So you're going down a relaxed fit. So sliding fit, look, a gap of 25 microns. So a gap of 1,000. That's the sort of free play, or like the space where oil can get in, with a tolerance again of about a 1/2,000th or 12 microns. So in here we got a lot of leeway, and that's just a close fit, right? So if you want something that you can grab and like spin and it'll sit there and spool down, look, you're talking 50 microns or 0.002 just for the gap, and then a whole thousandth or 25 microns just in the tolerance, right? So that's why when people get all crazy about like doing up their mills to like split thousandths and you're measuring in 10,000ths, it's like, you know, there's not a whole lot of parts that use that. And if you want, you could put oil or grease in there and these get even bigger. All right, so by contrast, let's look at like precision space, okay? So this jet engine, the sort of the tightest tolerances, and granted it's largely because it's huge and your tolerances need to get bigger, but you're talking tolerances on the order of 10 micron for the manufacturing of it. Where it gets tough is when you try and measure those parts coming off the line. I need to measure to 1/10 of this, so right, so my measurement machine needs to be on the order of 1 micron, okay, not 10. So that's, you know, if 25 micron is 1,000th, what, you know, like 1/25th of a thousandth in order to measure these parts coming off the line, right? So again, am I making pretty pictures or sort of pretty parts in a design studio? I'm on this spectrum. If I'm making like a steam engine or boring out a piston in an engine or doing journals or anything like that, these are the types of tolerances that I see. And if you're off the deep end in sort of high-end manufacturing and you want to split hairs, you can do it. But this space here is super expensive, super highly specialized machines, things like that. So yeah, you can make machines do this, but I recommend shooting for this, and if you could squeeze these tolerances out, do it, okay? So here's where the line starts to blur between elegance, which is beauty and simplicity, and masochism, which is the practice of seeking pain because it's pleasurable, okay? So when you go through this software correction process, keep this in mind. Like, there's a big difference between elegance and pain, okay? And trying to make things perfect and trying to do things the best you can is extremely painful, especially if you shoot for that first, okay? So I highly encourage you to focus on simplicity and get it to work, okay? Do all your geometric errors first, get it to work. Then maybe add some dynamic errors. Get it to work, then sort of focus on all the rest of the stuff. So, okay, so don't be a masochist, keep it simple. I'm not a sadist, I don't want you to feel pain, okay? On this slide, I have some sort of examples of machines and talk about a little bit about, you know, what to expect and sort of why they're like that and things like that. So in this sort of homemade rep wrap machine, you can sort of see there's all types of materials, right? There's steel all thread, or whatever you want to call it, threaded rod. There's sort of plastic 3D printed joints, okay? Look, they put all of their sort of driver electronics right on the machine. And sort of, where are their stepper motors? Okay, they're mounted to like plastic. So this giant heat box is mounted to a plastic part. Again, if you're just doing like pictures of your face and stuff, maybe that's fine, okay? But I wouldn't try and push any precision on a machine like this. So let's look at sort of the coefficient of thermal expansion, CTE, of steel versus plastic, right? So obviously steel is going to be more stable, and that's why they make machines out of steel, okay? The equation's pretty simple, right? Like, so you have length times the temperature difference times the coefficient of expansion gives you how much that part is going to expand or contract given those conditions, okay? Or from its original length even. So for every 100 millimeters and 10 degrees Celsius, okay, steel, the coefficient something like 10 to the minus 5, gives me 10 microns of growth per 10 degrees Celsius, okay? So I've seen stepper motors get up to like 100 degrees Fahrenheit or 150, which I don't know, what's that, 75 Celsius, something like that. But let's look at plastics and things under those same conditions. So for every 100 millimeters, every 10 degrees Celsius, now my coefficient of thermal expansion is an order of magnitude higher. It's 10 to the minus 4, something like that. Okay, so for every 100 millimeters of part, I have 100 microns of growth. That's 100 microns. So if your whole tolerance is 25, you're out by a factor of 4 per 100 millimeters. So look at this sort of goofy machine with all this plastic in here, right? So, and that's per 10 degrees Celsius. So this is crazy. So anytime I see plastic on a machine that's trying to get tolerances anywhere near 1,000th or 25 micron, like, it ain't gonna happen. Not unless it's super stable environment and it's like very carefully engineered and things. So let's just look at this Haas machine, all right? So it's, first of all, when they cast these bases, they like cast them and then leave them outside for a full year for all that stress to kind of resolve, and it sort of weathers, and then they come in and start machining it to set the rails and build the machine. That's pretty crazy, right? And look at it, it's just super simple. There's no, all the controls are somewhere on the back of the machine, probably not anywhere near the frame. They're isolated, there's cooling fans, okay? So like, this gives you an idea, like, shoot for this. Don't go building a machine that looks like this because it looks cool. Like, it's not gonna work. Not only that, look, it's Cartesian, okay? Your axes are like aligned with your coordinate system. So when I put in like an X part coordinate change, all I probably have to do is move the x-axis, okay? So what are you gonna do when you're talking about all these linkages and all these different axes, okay? So what are you saving here? It looks cool. It looks real cool. And look, got a pop can, and we're making Klein bottles, and I'm probably a mathematician and I love that. This is masochism, no go. Build a Cartesian robot, build it out of steel. Good. Good, bad, okay? So there's kind of a lot on this slide here, and I hope that I had a little bit more time to kind of go in this, but maybe we can make sort of an advanced video on some of these crazy setups here. But sort of back to like the error budget, and really this video is for you guys, and I think a lot of this is sort of entertainment and just satisfying curiosity. But if you're going to software correct a machine at home, we're probably going to be kind of over to this side here using some simpler sort of things, right? So gauge blocks are cheap, and all that is just a piece of rectangular steel with two parallel faces that are ground to, you know, collectively like atomic, maybe not atomic, but a certain number of wavelengths alike depending on the grade. And a lot of times, if you really need a lot, you can go to like an optical flat. So gauge blocks, they're pretty rough on top. So if you're using like a micrometer or something, the contact area is pretty wide, so you can average over that roughness and it doesn't really matter. But if you're using some kind of light-based sensor or really small contact patch, get yourself an optical flat, okay? And if you go small and things like, you know, these DIY machines, they're small, the parts we make are pretty small, things like that. So when you're going small, these are totally affordable. Optical flats, maybe a couple $100 for a small one, but if you really want that, that's kind of what you're going to have to do. Okay, so on the sort of other end of the spectrum here, 1, 2, 3 blocks. Okay, they make these things, they pump them out probably in China and all over the place, and you could probably find them at garage sales and things. They put thousands of them on a machine and do them all at once. So the cost for these things is super cheap, and they're awesome. They're like, you can get them for 20, 30 bucks with, they're split in tenths across the whole face and perpendicularity and things like that. So these are awesome, and they're huge. 1, 2, 3 blocks, you can get, you know, 2, 4, 6, whatever you want. And if you have buddies in a machine shop, you can have them make whatever you need. And it just, if there's a surface grinder, they make these all the time in school. I mean, so they're everywhere. So these are key, right? But if you really want to spend money on some sort of specialized stuff, they do make precision squares where you can get perpendicularity and things, and you can get them made in ceramic and with really high surface finish. can make them in like exotic materials, like Zerodor, for example. It's a material that, like, we'll just to simplify it here, we'll say every other atom has a coefficient of expansion that grows with temperature, and then the one right next to it shrinks with temperature. So the net effect is a zero coefficient thermal of expansion, right? So they're super expensive, but they're out there and you can find them. Of course, you got to measure something, so these are sort of artifacts to be measured, and then you're going to measure it with something, and most likely you're going to use sort of like dial gauges or line scales, and line scales to me include the scales like on a machine, or even calipers used in a nice way, or you can make your own mounts for line scales and use sort of an auxiliary one so you could float it around on top of the table. Things like that. So on the sort of farther extreme, I said I would talk about what's available. Grid encoder, really what it does is the plate goes down on the work table, right? And it's a silicon wafer usually with an etched grid in it. Okay, so it's like a line scale but 2D. And then you put the read head in your spindle and then drive it around over the wafer, and it sort of like clocks in 2D where you are in space, okay? And then you can do things like drive in circles. Well, is my circle, first of all, is my circle round? Is it elliptical? Is it jagged in certain spots where, like, I might want to slow down the machine when I'm running sort of at a 45-degree angle, or say like my X and Y have to do coordinated motion in, right? Like the servo error kind of compounds. So you can kind of map out machines. So a ball bar, extensible ball bar, is another example. So it's an instrumented sort of spring that rides between a sphere that's sitting on the table and a sphere that's in your spindle. And then when you drive the spindle around, say in a circle or like a sphere or whatever your pattern is, you measure sort of what that radial error is. You measure the separation between those two spheres as you're making this path, okay? So then you map that out, find out sort of characteristics of the machine. In here is a spindle analyzer from, this one happens to be from Line Precision, and this one is awesome. And we use it on sort of a lot of machines because it's 5 degrees of freedom all at once, okay? And it's sort of like these cylindrical things with the wires hanging out are capacitance gauges gauging off of a sphere, okay? So it's like really sensitive, and then there's 5 of them. There's 2 on the top sphere and 3 on the bottom. So they come in from the sides, and then on the bottom one there's 1 coming in. So if that spindle moves up and down while it's running, you're catching it with the bottom one. If it has sort of an angular wobble, you get it between the difference between the bottom and the top. If it's moving sort of anywhere in the XY plane, you see it both on the top and bottom. So it's a little bit tricky to set up, but what's really cool about that setup is you could drive the spindle in there, sort of do its thing, come back, put that thing in a tool changer, do some machining, heat up the machine, run it through its paces. Careful not to get coolant on this thing because the dielectric constants needs to be clean, okay? Your sphere needs to be spotless. So just keep that in mind, be very extremely careful, but you really need to be sort of not machining, but moving that machine around to sort of exercise these axes to heat up that machine just like you would. But anyway, then you can drive that thing back into this nest and see what happened to that machine, okay? So it's a really handy tool. And then on the bottom here is, that's just I say that's just an interferometer kit. This is like the staple for all initial characterization, okay? And these kits come with beam splitters and Walston prisms and all sorts of things that help you decouple individually all your errors out of the machine. So right now it's set up for, there's the lasers in this one, it's even out of the machine, okay? So that's looking through the laser heads pointing through a window and probably in the side of the machine, okay? Your beam splitter and interferometer leg is mounted in the spindle, and then your cube corner is mounted on the table. And what you're doing is when you move the table, you're measuring, in this case here, they're measuring the linearity of the axis. So what happens is that interferometer can count sort of how far that thing traveled. But what's interesting about this is if there's other errors in that table, the only ones that will show up are roll along Y if this is the x-axis, because what's going to happen is if this table sort of tilts, even though it doesn't move, it'll show that reading on that interferometer, okay? So, but it won't, if it moves in Y, it won't pick it up. If it moves in Z, it's not real sensitive. So it just might be a good time to point out that anytime you're measuring your errors, you want to do it where you normally manufacture parts, okay? So that's why they're doing this sort of up off the table, right? They're not measuring on the table, they're measuring where the part would be and then shooting the laser through that. Well, we kind of go into maybe some more of this in another video because these are already so long. The sort of final thing that you really want to consider is how complicated do you want this to be, okay? And keep this in mind, like I didn't invent this, okay? There's papers all over the web. Look, this is from Asian Institute of Technology, okay? Talking about force error, like errors derived from like machining force, loading that machine, and then how to compensate them. Like these papers are out there, okay? What I don't really like to see is sort of Asian Institute of Technology. So I'm part of International Precision Engineering Society, and you know, there's a lot of great things going on over there, but from a US perspective, and especially from a European perspective, it's like it used to be that things went over to Asia and India and Malaysia and things to sort of get made cheap because they had cheap labor, right? Well, that's not really the case anymore because that's where the money's going. Guess where the research is happening? Oh, over there, right? So we're sort of, I don't think we're losing the battle by any means, but they're not far behind us, okay? But anyway, like I said, these concepts are well documented, and if you do a little search in sort of academic journals and things, these pop up everywhere. But what I'll say is everybody has their own sort of methodology, right? So in this paper, they might, you know, to get it all into 4 or 8 pages or whatever this thing was, they really leave out a lot of the strategy and things that I tried to talk about in these videos. So, but one thing that I really want to point out is, look, they're using HTMs, right? So it's like, there's nothing new here. If you followed these videos, if you were brave enough to sit through 3 hours of lecture, this is all discussed, okay? So you should be able to like pick up this paper and understand and follow it. And maybe not like follow it exactly, but grasp the concepts and like read it like it's a newspaper and be like, oh, well, that makes sense, right? So I just want to let you know this stuff is out there, but you really need to consider like how much effort you need to go through to hit your tolerances, okay? So I would leave these again for like maybe that 3rd or 4th iteration of adding fluff and adding stuff to the software after it's already running, and then you can test it. Like, is it good enough? No. Boom, let's go through one more layer. Is that good enough? No, let's go one more, okay? You would think that the bulk of this video should be me showing you how to tram and sort of specifically how to measure and measurement techniques, but I think that there's enough videos out there on how to measure things. You know, one example is tramming a vise on a mill, okay? So is my jaw perfectly straight? No. But when I put my dial indicator in the spindle and then tram along the vise jaw, like it's gonna come in and out and sort of it's gonna follow all the stuff and like, oh, there was a dent in my vise jaw that I picked up on my dial indicator, right? But the concept here is like average line of motion, okay? So if I start out at +2 and I'm -2 by the middle and then back to +2, on the other side of the jaw, like that's aligned, say, with the x-axis. It's probably as good as you're going to get with that. Okay, so I'm not really going to talk about measurement. Like I said, there's tons of videos on that, but let's talk about sort of measurement concepts. So here's an image of a production setup from a person, you know, that you probably know in this space on YouTube, CNC. All disclaimer, I got this picture from somebody who got it probably from him, right? So like he's an excellent resource. I highly recommend his channel. But let's just sort of look at his setup. What's he doing here? He's got an indexing plate bolted probably to the table of, I think he uses the Tormach machines. You know, some kind of tool in the spindle, a drill or something like that. And then he's got this sort of array of what I'm going to assume is production parts. I mean, he makes like knives and things. I don't know what they are. It doesn't matter. But look, that fixture plate is in a vise. Okay, so that's fine. Okay, however you're going to normally use this machine is the way that you want to software correct it. Okay, but what I will say is, though, if you take this vise off, you got to do it again. Okay, so maybe it might be best to sort of gain that flexibility is to do it from the table, and then the only thing you have to redo is from the table when you put that vise back on. Okay, it's just like tramming a vise or whatever anyway, but you're kind of going to do this through all the sort of offsets and errors and things because it's a CNC machine. So normally you do this when you come in with your your wiggler or whatever, and you come in index a hole. You do that on the part or some feature on this fixture plate. It's that same concept when you do your work offsets, but you're doing them, remember, in the code that we're going to write that's going to intercept the G code prior to it even ever getting to those work offsets. Okay, so this kind of, once again, just like your tool selection and all that, needs to be thought of up front. So for me, when I'm doing CNC stuff, my vise almost never comes off the table either. So I think it's perfectly fine that he has his fixture plate in that vise. And what I would do, and what I'll show, is like you could put your stuff in the vise because that's how you're going to use this machine, right? So don't go crazy tearing your whole machine apart to like get all these elements and things. Don't do that. Just think about how you're going to use the machine and then go from there. Okay, so here's an example of like ultimate precision, right? This is a CMM fixture. So what they do is this sort of boomerang looking thing gets bolted right to the granite of the machine. And then they have these removable fixture plates that kind of like go into that sort of fixture that's bolted to the thing, right? And then also notice they've got this rotary axis also bolted to that. So here you're going to bolt this thing on and then calibrate to this. Okay, and then this, everything that goes in there becomes sort of like a part offset or an intermediate to a part, things like that. And again, it's repeatable. So we're going to calibrate to this and like calibrate our rotary axis and all that stuff, and then we can take our parts in and out. And notice on the fixture plate, there's all sorts of other fixtures and things like that. So in my code, I would probably like do object-oriented programming and say like, okay, so my object is a fixture plate number blah blah blah, and then on that plate is sort of sub-fixture this, which would be sort of another object, and then that's sort of an easy way to manage that, right? Because then you could always take this fixture, this like sub-fixture off of this big fixture plate and put it on another one. You don't want to recode that, you just sort of transfer this around in object-oriented programming space, okay? So in summary, if you have a CNC 3020 like what's sitting here, there's no vise at all, it's just sort of a flat bed. Well, it's like, well, scribe a line there, put a sphere, drill a little tiny hole, and call that the origin of the machine always, or maybe you have home and limit switches so you can sort of run it to home, and then that position that it sits in home is sort of like the 0 point of the machine. The problem with doing that is even though homing switches are nice, they're not really as repeatable as you think they are. Okay, so maybe on your machine they are, I don't know, but you need to kind of think through all this stuff. But however you're going to use the machine, that's how you're going to correct it. Remember that the goal, the ultimate goal here is to build this kinematic chain. Okay, so remember when I said like you're not going to tear apart the machine. So for example, again, this is from part 3 of the video series where I really kind of go through and explain this. You're not going to take the W-axis or the Z-axis off the frame. You're going to leave all that together, and that just becomes your chain. But what changes is maybe like you have a secondary Z-axis or like that rotary axis that was on that fixture plate. Okay, and then that's in between sort of the X and Y in the part, right? So you kind of have to, the goal is to leave as much of this chain intact as possible between sort of setups, and then only have these sort of these chain fragments that you have to redo when something changes on the machine. So sort of let's skip all of the rest of what's going on here and just focus on this sort of kinematic chain. Remember, that's the goal. You're gonna, like, what is your strategy to software correct this machine? So I said that this laser, sort of the interferometer kit, is the sort of the gold standard for how to software correct machines or initially calibrate or characterize a machine. You're not going to go out and buy this. So the next best thing is to put some known shape into the machine and then sort of use that to kind of measure, you know, if you were to, you know, put your dial gauge in the machine and then tram along one of these flat faces and you don't see any movement on the dial, it means there's no errors, right? So you don't need a direct measurement technique to be able to sort of decouple every single error. You just have to be smart about where you put your dial indicator and what you put in that machine and where. Okay, so what I'll say is it's a lot easier to do individual axes and isolate individual error terms with the interferometer kit, because that's what's available, and that's sort of that's what's sort of industry uses time and time again. So there's a lot of R&D and a lot of technique and a lot of things that go into this. But again, what they do even on CMMs is after all this is done, this is how they check the machine periodically, right? They put these in there, and then also even with CMMs, they do these, they have like a go button, and it sort of takes measurements all over this this known part, which again, this happens to be zero door. Okay, so this super stable known geometry part, and then when it measures wrong, it automatically corrects the machine because it knows what it should be and all this stuff. So you can have auto sort of correction routines even with this. So even though this is the gold standard, the difference between putting an artifact in the machine and measuring it versus isolating each axis and each error and characterizing it individually is just that. This, you're going to really have to think hard about what you're measuring and what influences are going to be into that measurement, versus this, you can separate them out and easily decouple them one after another. Okay. The third thing is cut a test part. Okay. So this example here is in the aerospace industry. I think NAS 979. If it's wrong, I'll put it in the words here. But what this is a 5-axis part, and I'm pretty sure that the code or the standard says it needs to be hand coded, but that's insane because this is a 5-axis part. If you notice, this ramp here around the part is actually on a tilted plane. So I don't know too many people that are going to be hand coding 5-axis parts, but nonetheless, there is standardized things, and they call this the circle, diamond, square test. Okay, so the square is on the outside, and then there's a circle sort of as like a birthday cake thing, and then there's a diamond on top. Okay, and what this tells you here is my linearity correct? Am I cutting that square? Is it actually square? Is it rectangular? Things like that. What's my surface finish along that edge? Because I'm only hopefully using one axis when I cut that. Okay, the circle tells me how fast the servos and the controller can sort of correct for changing velocities and coordinating motion. So is it circular? What's the surface finish? Is the step height correct? Things like that. And then the diamond up top is a linear coordinated motion move to get your facets on the diamond. And again, that tells me how consistent is it. So a circle tells me how fast I can change, but the diamond tells me how stable that trajectory really is. So the surface finish on the side of that can tell you a lot of things. Again, is it sort of, you know, is it a rotated square? Like what's the dimensions of that? So again, and I think the standard probably describes all of that, and you could probably get it online. I wouldn't recommend buying it, but I'm sure that it's old enough now that there's a ton of review material on it, or like cliff notes and things. But anyway, these things exist. So cut a test part, right? And if you're in production making parts and that's all that machine does, or you spend a lot of percentage of time making certain parts on a machine, well, like use that part to correct the machine, right? Or to at least correct the G-code, right? I mean, they do this all the time with cutter compensation. So again, as this is for like the DIY community, let's assume that you can get your hands on a 1, 2, 3 block or something like that. And again, if it's just a flat bed, bolt it to the table, or, you know, if you're sort of like, well, I normally bolt my fixture down and then my part sitting on top of the fixture will raise that block up, okay? Get it to where your parts are normally made, okay? And then that eliminates sort of roll errors and things like that, okay? That's called the ABBE offset, A-B-B-E offset, okay? So, and then our measurement utensil for the DIY community is almost certainly going to be a dial gauge, and this one is the sort of the sensitive type that has the feeler sort of on a pendulum type of thing, and you can get these that read in tenths. You know, I think even at Harbor Freight you can get ones that read in 1/2 thousandth, and you know, these just tend to be a little bit more sensitive than the plunger type dial indicator. But in either case, let's just assume that this is going to be the setup to characterize a machine. What's happening here when you place this perfect part, okay, so if it's a Cartesian or perpendicular cubic or whatever the word for a 3D rectangle is, the goal here is to say wherever that thing lands, that defines the coordinate system, okay? And this is a shortcut over what I talked about last time, because you're not finding sort of average line of motion for all the axes and then defining them individually. It's like wherever that is the coordinate system, okay? Because we're going to assume that that object is perfect, and wherever it lies defines the coordinate system. So it's a shortcut. It's not as good. It's a shortcut. But for the DIY community, I'm pretty sure that it's a worthy shortcut. So again, don't just slap this thing down in the middle of the table. That makes no sense, okay? So ideally, right, your x-axis of that thing, if you're running sort of any kind of Cartesian machine, you want the x-axis of the part to closely align with the x-axis of the machine, right? So when I want to move in sort of x part coordinates, I just move the x machine axis, okay? So again, just like tramming a vise, and if you tram your vise and then put this into your vise, like you already did that, right? So it kind of just makes sense that wherever this ends up becomes the coordinate system. But don't just put it anywhere. Think about where you're putting it, and you want it to be, again, in the same spot as where your parts are going to be made, and in the orientation that makes sense for the machine. So for example, the height of this is only 1 inch, right? If this is a 1, 2, 3 block, my width is 2 and my length is 3. So my critical axis is going to be X, because that's what I tram my vise to normally. That's where my longer cuts are. I want as much measurement length on my x-axis as possible, okay? So And usually my parts are not as tall as they are wide, so I'm going to choose to lay this thing down, and that's why it's in this orientation. But maybe your machine's different. I like a 3D printer, I normally stand things up so that my every time I do a layer, it's as small as possible so I can build this thing up faster. Whatever orientation makes sense for you, that's how you're going to put it on, okay? So the goal then, or the simplification then, is going to be, this is really important. At machine home, you want the spindle to be sort of, or whatever, the tool holder to be over the XY origin, okay? So, and the reason you do that is because you don't really want a linear offset between your coordinate system for the machine, okay? It makes no sense to do that because you're going to have one for your part anyway, okay? So your fixture, for example, you're not always going to have the first part sitting at the origin, and then for an array of parts you have a part offset for each one. So this is, remember, this is machine coordinates. So I want, when I fire this thing up, and if you notice, the spindle's pretty much over the z-axis in this position anyway. So first criteria is at machine home, okay? I want my origin to be right under the spindle. And then for things like garble, I don't think you have a choice but to use machine home as your starting point, because when you reset that thing or run the program, it kind of goes from 0, 0, right? So again, unless you have the homing operation program, whatever, but just make things simple for you. When the machine's at home, put that, that's where you want that, okay? The coordinate system for the part origin is where the tool intersects with the plane 2 inches off the table, okay? Right? And remember, like, that's because, oh, I normally have things in the vise, and then I normally have my part, and my part's sort of this tall, so that's where I'm going to say the origin is where the tool intersects the plane of the table or the vise or whatever, and then I'm going to go plus 2 inches from there. Then I'm going to say my x-axis is defined by the average line through the limit of travel, or your ability to measure that, okay? And remember what I said, like, oh, there's a dent in my jaw, like, it's not going to be perfect, but just take the average line of motion, okay? That's okay. And then this is important here. XY plane and z-axis is defined by the faces of the 1, 2, 3 block. So again, if your table is not flat, or if your fixture has sort of a tilt to it, you kind of want to replicate that, right? Or you kind of want to say, like, well, if my vise isn't ground right and I'm using a vise, or if I have multiple vices, take it off and just use the table, okay? So again, this basically just means wherever that block lands, that's the coordinate system, okay? And then because we have the kinematic chain with all these other coordinate systems, we just simplify and say all other coordinate systems are co-located and aligned with the previously described part. So just because the x-axis is bolted to the y-axis, and they're not, like, the line of travel doesn't sort of like go through each other, and then that's bolted to the frame, which is sitting on the floor, and then my z-axis is bolted to that. It doesn't matter where the origin is completely arbitrary, right? It's kind of like vector space in math. It doesn't matter where, you just have to say, like, when I move 2 from machine home, it's going to go from that arbitrary point 2 in the x direction, okay? So wherever you define the origin is completely arbitrary, just like G54 offsets. That's why they're there, it's arbitrary. And that's sort of, you know, where you're at here. So we're just going to simplify and assume that they're all co-located, okay? When the machine's at home, all those coordinate systems are perfectly co-located. This is where I had grand visions of bringing you in on the machine and, like, setting up the dial gauge and showing you what the reading is and stuff like that. But, you know, I don't think that that would be very entertaining, so we're just going to kind of keep focusing on the concepts here. So what I have shown here is a setup gauge block, okay, or I'm sorry, 1, 2, 3 block, and then sort of the three, our Cartesian axis defined by wherever that block is. So if I want to measure the geometric error with the rotation about z, right? So again, I'm going to move the x-axis, so this corresponds to how aligned is my x-axis to wherever I bolted this block, okay? But remember I said that you can't individually isolate each error, so what you're also going to measure, or what you could choose to ignore it, but that information also means that you now have a map for the dynamic error as you're moving this along with respect to the y direction if I'm measuring perpendicular to the y-axis. Okay, so that's why it's really important to, when you're tramming a vise, the scale doesn't matter. So however you have your dial indicator, as long as you're looking for that average line of motion, it's fine. The scale is completely arbitrary, but in software correction, it's not. So you have to make sure that you're indicating perpendicular to the face, okay? So that with the wiggler, it needs to be in the plane of the face, with the wiggler on the face itself, and with the wiggler sort of straight down, okay? Don't if this is my wiggler sort of like this, don't put the indicator way out like this, because now as this moves, I have an angular error in there, okay? It needs to be straight, and then I'm going to kind of do that. And that matters because the scale here matters for both of these, okay? So again, I'm going to indicate on the x face looking into the y-axis, and I'm going to move my x, and I'm going to move my x machine axis. So this is the result, okay? So the blue we're going to call the indicated measure here, okay? The sort of wavy line is the actual path that the dial indicator travels along the face. And then we're going to assume that my face is flat and that it's here, okay? So what I'm going to do is I'm going to say I'm going to divide that into like 10 increments or whatever. I'm going to, maybe you have a really long straight edge, so you're going to kind of pick whatever makes sense for you. But I'm going to probably say that there's not going to be a whole lot of like high frequency ripple in it. It'll be like the axis might be bent, but it'll be like bent in one banana, right? So you don't need to divide this into 1,000 steps. You don't need to move one step on the stepper motor and take a measurement, because you just really care about that low frequency sort of ripple, okay? So for example, I'm going to divide this motion into 10, and okay, notice that these lines are perpendicular to the x face, okay? Not to the x motion. So that introduces a little bit of a cosine error, but it's okay. It will be close enough as long as your machine is better than, or as long as your machine is more right than it is wrong. Okay, so when you have your 10 measurements, you move the machine along whatever, and you say, okay, so I moved a total of 3 inches. You can't do that with the 1, 2, 3 block, but let's just make it simple. I moved a total of 3 inches. What's that, 75 millimeters? And then I'm going to divide that into 10, and then so that, works into whatever it is. But then you say, okay, I chart that in Excel, and I pull an average line. I calculate the average of that, the average trajectory. Okay, and that gives me the angle in between my x-axis average line of motion and then the true x part axis. Okay, so that's going to be one of the geometric errors. So my part is rotated by this number away from the part axis or machine axis, right? That's the difference. So the farther I go out in this example, the more I need to correct in y to get it back to where it needs to be. But then if you don't choose to ignore it, now I have the residuals. Okay, then the residuals become my dynamic error as a function of how much I move the x-axis in the y direction. Okay, so this is a linear dynamic error relative to the y direction as a function of my x machine axis. Okay, and then this should make sense kind of as you go through in your own machine. Alright, and then when you're done with one, you need to do every single setup to identify whatever errors you think are important. Okay, you don't have to do these all. Like, so I would think like, okay, so squareness of x and y, perpendicularity of the xy plane to z in both around x and y axes, linearity. You know, typically if you have good axes, normally they're pretty straight to within a thou or two, and a really good machine probably a quarter of that, or you know, for the metric people, a thou is again 25 microns. So again, you don't have to do all these, but I put this on here to kind of iterate sort of what the different types of setups isolate, which errors they isolate. Okay, so we talked about this one, we indicate into y, we move an x. This one here, we put the indicator down on the top face, and again, move in the x direction, and that gives me rotation around the y-axis, right? So if this block was sort of tipped down around y-axis, right, again, using the right-hand rule, if my indication grows as I move along here, that means my part has a positive rotation around the y-axis, okay? And then again, that's a geometric error relative to the x-axis. But then if you take the residuals, that's the dynamic error in the z direction as a function of my x-axis, right? And that's kind of like this hop and skip. And what I'll say about that is ignore the high frequency stuff, because that's generally not repeatable. And again, when you take those measurements, do it 10 times and then average each one of those too, because so for example, if you had 10 bearings underneath on a perfectly flat surface in a perfectly flat way, but the bearings weren't round, like sometimes it'll rise, sometimes it'll drop, and that won't be repeatable. Because if you move 1 inch and then move it back, and then move like 7 inches and then move it back, or like 3 inches and move it back, those bearings are in a different spot depending on sort of what the previous history is. Not that it has a memory, it's just a deterministic system. So ignore really high frequency stuff. That could be bearings, it could be roughness in the ways, it could be whatever. So just sort of keep that in mind. You're just focusing on the low frequency changes and stuff like that. So again, these two errors. Now the difference between this setup and this setup is here I'm still moving my x-axis, okay, but now I move my indicator instead of over or near the x-axis itself, I'm going to move it in y. Okay, so what that tells me now is roll around the x-axis, okay? And you need to move that out. So now my dynamic error becomes a function of x and y. Okay, so this is where you start building that 3D map, and then maybe do this 10 times. You know, I don't know if I would really recommend that, again, especially not at first. Kind of come back to this one. But in the end, this one's not enough to give you information about roll around x as you move x. You have to offset your indicator to catch that geometric error around x, okay? And then your dynamic errors, again, if your table twists and is also bent, you need this to decouple that. You need to do several to kind of pick up that bend along y with the twist along x, okay? And then, again, same thing for, now I'm going to move my indicator and I'm going to move my y-axis now, okay? So I indicate along the y face and move this. That tells me, again, rotation about z of my y-axis, right? So that this also tells me squareness between x and y. And then dynamic error as a function of the y machine coordinate, okay? Same thing, I move it to the top, but I keep it over as close to the y-axis as I can, or the origin as I can, and then same thing, I offset over and I pick up and I start mapping out as a function of x and y, and I get dynamic errors with respect to y as opposed to with respect to x, okay? And then again, this goes into z and whatever other axis you have, but again, you don't have to do them all. Just think about what errors are important to me and how I would go about setting up to measure that, and then also consider that with this method, it's extremely difficult to just identify one of these, and that's where that interferometer kit really comes in. So keep that in mind, really think hard about what else influences this measurement, and only move one axis at a time. So here we're moving x-axis, here we're moving the y-axis, and even though you sort of have this function of x and y, I'm only moving x, and I'm only moving y, okay? That's very important. Once you have all of your error terms, then you can come back to this slide that was in part 3 and start implementing them in an order that makes sense for every single element, okay? And remember, your order of permutations matters, okay? So your rotations, in this example here I have, you go from coordinate system A, you go from A prime, which means I roll around X, and then roll around Y, and then roll around Z, and then that gives me coordinate system B, okay? So my geometric errors, angular errors around X get put in first, and then Y, and then Z, right? So, and then you go through and add in all of your sort of, first it would be geometric, and then measured, and then dynamic, and again, these could be in any order, but you just keep that consistent, okay? It's going to help you. And then what that gives me here is a transformation from A to B in this example with all of these terms, okay? So here I have geometric errors, here I have measured motion, and then here I have dynamic errors, and then all the rest are omitted in this example, but you could sort of go through at your own pace and try and figure out what they are. And again, coming back to this slide here, the important thing to remember is this is your kinematic chain, right? So for all of these things here, I have a simple transformation from part to my sensor coordinate, and I just basically, this is like basically at machine home, right? And then I have to add in my measured motion, so it gets a little bit longer. And then if I want to add dynamic errors, they go in here as a function of that measured motion, right? So you can see when I say start out simple, just start here, then add measured motion, then add dynamic errors, right? And then let this sort of cascade out to make it as complicated as you want, but again, start simple. Don't be a masochist. If you remember, what we're going to do is after you CAD your part and set up all your CAM and export and do all your post-processing, just before you send the G-code to the machine, you're going to intercept it, and then we're going to write a new G-code file based on machine coordinates and not part coordinates, and then we're going to feed that into the machine. So the software is going to have 3 parts. Actually 4, but 3 main parts in the software. So, and it's really simple. We're going to read the old one. We're going to transform it from part coordinates into machine coordinates. And when I say machine coordinates, it's actually like axis instructions per axis, right? And then we're going to take that transformation and push it to a new G-code file or overwrite, whatever you want to do, and then send it off to the machine, okay? So when I say there's 4, it's because always with programming you write functions, you have declarations, that sort of stuff. So going through this, here at the top, you put in all of your offsets and errors, right? So these are the measured motion, and rather than putting it into HTML, homogeneous transformation HTM form, you can just, what I do is I leave it as linear X, linear Y, linear Z, rotation about X, rotation about Y, rotation about Z. Okay, those are my terms. Those are what I call offsets and errors. Okay, and I leave them in that form because it's concise. But that's not how we do the math. So what it is look, it's nested into a function that says get HTM from this 6 parameter list, and then save it as some function, and then just out of to keep notation right, I save it as transformation from my tool to my Z coordinate system, right? So right here also is where you have your tool offset, right? That's T to Z. In this case, on the CNC 3020, the tool's on the Z axis, so you have a transformation from Z, or from T to Z. Okay, and right now I don't have anything in there. And then equivocally, okay, so from Z to X, look, I have 1 error, and then from X to Y, I have 1 angular error, and then from Y to P, I have 1 angular error. Okay, you get the point. And then you have to define some point of interest on the tool. So you can say like the point 0, 0. So imagine this thing is like a pencil point. The 0, 0 coordinate would be sort of at that point, or maybe it's at center of the rotational axis flush with the spindle face, so that way when you put in a tool, you can just measure that tool offset and you can put that in there as a minus, Z or whatever you want to do. So you can either put your tool offset here or here. Now on 5-axis machining, that's not what you want. You don't put that 0 in there, because if you have, say, a ball nose cutter, well, I want the edge of the cutter to touch my part, right? So what I'll say is most post-processors, so let's say like Mastercam and things like that, they already compensate that. So it's not, it's where is the center of the tool in part coordinates. But that really means, like on a Cartesian machine with no errors, then when I want to move my axe, I just tell the x-axis to move. Here on a machine that's not perfect, you have to do a little bit of thinking there. But so keep that in mind. Most post-processors already compensate for tool offsets for you, and that's why you have to pick your tool in there. So leaving it as 0, 0, 0 in most applications is fine. All right, so this function here is the function for this function here is the getHTM function, right? So it takes my parameter list and then it returns an HTM, and it does that again keeping in mind my order of permutations. So in here again, so I think in degrees, who thinks in radians, but to keep your processing fast, convert to radians once and only once, right? So we're going to convert, and then we're going to say rotation, whatever, right? Rotation around X, Y, and Z, we're going to convert those to radians, and then I'm going to say, I just use this RET variable as sort of like a placeholder as I kind of permutate through. So here I punch in my identity matrix and then automatically just type in my linear offsets, because those in my transformation order are first. And you can do that in one step. And then I build each rotation matrix in sort of a way that's easily visible, and then at the bottom here I take the dot product through my permutations. Okay, so here I'm saying n dot, again this is my RET, just my return variable, it's just a placeholder for whatever was here. In this case it's going to be the result of my linear transformation, and then I dot product that with the rotation about X matrix, okay? And then that returns and it gets plugged into the next, and then that one returns. So it just kind of cycles through, and then that function returns the matrix that's at the end of all of that. Just as sort of a precursor to what's coming next, I also have this transformation function, and what it does is it takes the, you tell it what position the X commanded coordinate would be, and the Y commanded, and the Z commanded, and then that point of interest on the tool, which again, remember for this application, we just consider it 0, 0, 0. And then it uses our kinematic chain equation to transform from the tool coordinate, using where that machine location is, to transform into part coordinates. So what this tells me is, where is my tool point in part coordinates, okay, given wherever my machine is that I tell it. Okay, so at machine home, this should be 0. But as you start moving the axes around, now it won't be, right? So what this function does is you tell it where the machine is, and it tells you where that tool tip is in part coordinates, okay, using the kinematic chain. So the way that this works is, again, my XM, YM, ZM, I just essentially add those in to one by one in return matrices. And then what I do is I build a tool matrix, okay, using I basically just reshape that array, because right now it's a list of 3, and I turn it into a matrix with 1 by 4 dimension, because remember our HTMs for a 3-axis system are actually 4, or even 6-axis system are 4 by 4. So we have to do 1 by 4, so I'm just really reshaping that, adding my 1 as a scalar, right? And we talked about that, I think, even in the second video. And then I just go through, just like before, and do the dot product as I'm permutating through my chain, right? And then I return, here I say n.asArray, so it returns as a 4 by 4 matrix, okay? Or, no, in part coordinates, so it'll be a 1 by 4 matrix, right? Yeah. So that's where it returns, and just if you're not familiar with Python, I import the math library to do sine, so I import it as m. So when you see, for example, right here, m.sine, that just says from the math library, use the sine function. I use numpy as n, so here I say n dot, I'm using the dot product in the numpy library. And later I use this RE library to search strings and things. It's called the regular expressions library in Python. Now that we have it set up, let's get into the first part. How do we actually parse this G code, okay? And here's the code, pretty simple, broken down, okay? So at the very top, I just open the files. I open the in file, I open the out file. And all that means is it's really just I open a reference and control whether I want to read or write or, you know, whatever, those types of things. And then there's also, like, by default, it sets the file location as the beginning. And if you, on the out file, if you don't specify read or write, I think by default it automatically deletes the file too, or empties it, and puts the cursor at the beginning for you to write. Okay, so if you don't want that, just sort of play with those parameters. Okay, so here I assume an initial condition. So when I hit go on the Python, because I'm using Garble, I automatically assume that Garble thinks that the machine, wherever it is when I start this, is at 0, 0, 0. Okay, so that's my first assumption. And just kind of ignore this for now. I don't even think I use it. But we'll talk about the inverse kinematics function later. But really, you just assume the initial conditions. So that would be like the tool, the point of interest on the tool, and then where the machine is when you start the program. Okay, then I set up my matching parameters here. And again, that was that regular expressions thing. I don't really want to go into this, but really all you're looking for is like X, Y, or Z. Okay, and then if you had ABC, you would build one of those for that. And then that's in a bracket, which means any one of those parameters. The plus just means, in the string, means we're going to look for x, and then some plus or minus sign, maybe, and then a decimal, okay, maybe a decimal point, and then maybe another decimal. Okay, so these are my matching parameters, and then that just really tells me, it's like I'm looking for when it tells me move in the G code, when it says x 3.1 or minus 3.1, it looks for that, okay? So, for example, x minus 20.1 or x3 both get found by this string using the regular expressions library. Alright, so we set up these, and then I go into my for loop. So I read this file line by line. So I take the first line, and I call it inline equals line, and then basically saying all of that line. Okay, so the length minus 1. So minus the termination character, which is, I don't know, /r or /n, depending on whatever whatever text file. So again, you might have to play with that. -2 if there's /r/n. Or if you don't want the colon in there, whatever you want to do, okay? Then from that line, you have to determine, like, was that a spindle command? Was that a, modal command or whatever? So you have to determine, was there a move commanded in that block? Okay, which is a line in G code. So here's where I use the regular expressions thing, where I say x. So basically I extract that string. So I say find all in the regular expressions x match, which we defined, and then in that one line, the first line or the next line, and then return it as x match. So I say if the x match length is greater than 0, that means that it's trying to command an x move, okay? And then what I also do is specify that now my x coordinate in my part, or my x coordinate in my part coordinate system, my desired, is I convert back to a float and dump it back into that coordinate, okay? And I do that for x, y, and z, okay? Then I say if there's a match in either x, y, or z, I basically say, okay, yeah, there's a move, okay? And then I say, solve the inverse kinematics, basically transforming that back into machine coordinates from part coordinates, okay? So that's the second part. So just as a refresher from part 3, the goal here is to get our machine to drive to this part location, right? Maybe from here, from 0, 0. If it's from the homing position to the first point, we have to go from here to here. But now remember, our x-axis and y-axis in this case had a squareness error by 45 degrees or something like that. So what we have to do, if we moved the x-axis and y-axis by that part coordinate, we would miss by some amount, depending on how bad the squareness error was, right? But remember that we know those errors, so what we can do is we can say, hey, let me simulate that move just in sort of programming space, and say, like, if I did command the x-axis and the y-axis to move by that desired amount, how far would I be off? Okay, and then that gives me, if I subtract or add, depending on how you set up your vector directions, I get an error vector, right? So if I, in this example here, if I add my error vector to my x commanded and y commanded, I should, and then, in components, x, y components, I should end up back at that point. But remember, my error is in x and y part coordinates, okay? So you just keep iterating this through, and the solution should converge. Okay, so that's the goal of this solve inverse kinematics function. So looking at the function here, the inputs are what is my desired part coordinate and what is my point of interest on the tool. And then what's it going to take to align, like how do I command my machine to align those 2 points? Okay, so here we're going to use that strategy. My initial guess, I'm just going to say, well, let's start from machine home. And because this is in a for loop, it starts from there every single time, but that's okay. So, and then I'm going to define tries as 50, so you could either tell it to do it 50 times, or you can tell it to just keep going until, the error is under what your error budget is, and that might happen in 3 iterations, it might happen in 100. But you're not doing any more calculation than you need to. Now, if your solution doesn't converge, that will crash your program or your machine. So having the tries at 50 just as sort of an initial way to get you going, and then with 50 iterations, I mean, it's going to converge to like machine epsilon in terms of the error anyway, but whatever. And then as a safe, sort of a safety check that back at the end of this and make sure you're within your limits on the machine, or you're like your safe zone, you know what I mean? So you're not going to crash it. And then, if it's wrong, then flag the program or break or whatever you want to do, right? So let's look at what's involved in this solve block here. So now, on a Cartesian machine, all solutions are singular, meaning there's only one way that you can move your x-axis, y, and z to align those 2 points. So I don't have to worry about checking singularities. I don't have to worry about any of that. And also, the way that this machine is set up, and if you think about it really hard, there's certain axes that don't depend on any other axis, right? So, for example, my y-axis is bolted to my x, so of course that matters. My y coordinate is going to matter on my x because there's an error in x, right? So I first have to solve for x and then solve for y. So you could do this all in one step, solve for x, y, and z. The solution should still converge, but you can also use strategy to minimize computation. So if you're doing this on the fly, you want to keep the computations as small as possible. So here I solve for my z-axis first because I defined my xy plane based on the plane of my xy axes on there. So where I put my block already is in the plane of the xy table, right? That's just kind of where I define it. And then again, that's an advantage of decoupling all the errors. So you may or may not have that when you set your gauge block on the tool because the table might not be perpendicular, right? Like if this is the table, the y-axis might shoot down or something like that. So this may not work for you. And remember, in the part 3, there is no easy solution. You just have to think through this carefully on how to solve. In this example, I solve for the z-axis first, then sequentially x and y, okay? Because my z-axis is singular, and then my x-axis was bolted to the y or whatever. So I just solve them one at a time. But all 3 are the same, so let's go through it. So for z in range from 0 to try, so 450 loops, calculate the difference, okay, and I'll kind of come over here, from this x form m guess t. So I'm transforming, given my machine guess and my tool point of interest, where do those align in part coordinates? And then I subtract that from the desired part coordinates. Okay, so that's the error. And remember, in my vector picture I add, and here I subtract. It's just a bookkeeping thing. And then I update my guess to add the error, right? So I say m guess 2, which is the z, plus the z coordinate in my error term. Okay, and then that just loops through and the solution converges. Okay, so breaking that out, reiterating here, so if p is the desired part coordinate and x form is the simulated part coordinate given the machine location or the guess, then my error is that xform return variable minus the desired part coordinate, and then subtract the error for new guess, and then iterate until it's 0. That's it. Remember, though, if your machine's not Cartesian, you have to think about singularities, and also for machines with redundant axes and rotation axes, any solution is not necessarily the best solution. Finally, let's look at how to get that transform coordinate back into the G code. Okay. So you remember we had this if move required statement, do all of this. Okay, so I'll solve for the inverse kinematics, which we just did, and then it returns an array that has the commanded x, y, and z sort of parameters, like move x3, move y2. Okay, and then we're going to, from that, parse it back using the sort of a string. We build a string from that, okay, and push it to a float, and then we basically concatenate those strings, okay. Then this split function here, the split function returns an array of any match that's in there, and what it does is it removes it. So say there's an X, Y, Z move in there, what it'll do is it'll take the beginning of the block, so say like G01 or G00, whatever, it will put that as the first array, and then it'll say X in the decimal as the second element in the array, Y, Z, and then finally anything behind it, like spindle, whatever. So what I do is I say for I in range, and then each element in that array, if I equals 0, sort of, like basically put in the string, you know what I mean? And then else, if not, then just add that directly. So here we're identifying that it was a match, and then we're replacing that match with our transformed and then reformatted code. And then here we write both to the screen and the file. And then once our for loop is done, all the lines, we just close the streams. And that's it. So it's not hard. And this code will be available in the description. I'll put a link. Might take me some time, but I'll get it up. If you're still here, if you managed to watch all 3.5 hours of this, I know it was too long, but there's so much to discuss. If you're still with me, or if you're really interested in this, please put a comment in there or message me. Let me know that you watch these, because they take forever to make, and the ideal time span on YouTube is like 5 minutes. Like, you're not going to teach anybody anything in 5 minutes, but I think YouTube's really for entertainment, but there's that whole lecture space. So when you push videos that are an hour long and nobody watches them, it kind of looks bad on the channel. So if this interests you, please throw a comment on there. I don't really care about statistics. If it helps people, I'll make more of them. But if not, then then we won't waste anybody's time, or web space, for example. But so if you're with me, you want more, please comment. Also, tell me what you think. Was it good? Obviously, they're too long, but again, it kind of just has to be that way to learn something this deep. But let me know what you think, and I'll see you next time. Thank you.